All right. First, let me pop out the chat. Okay, we're good. We're good. Welcome. So for the first half, so it's like people are pouring in. Let me just type out the agenda for today. Oh, cool. Wow, this is pretty cool. I could pin messages here. All right. That's so cool. Let's just go to Flex just for fun. Right now, I'm not sure how much you can see, but so you should be able to see this VNA view, and in the camera here, like down in the bottom left, bottom right corner, you should be able to see my my actual NanoVNA. So I've been trying to measure my NFC V1 board. Here's my V2. I haven't assembled it yet, so maybe we'll do some board assembly as well. But I want to measure. I want to see that frequency response where I get some gain at the resonant frequency that I tuned it to. And the kit that came with the NanoVNA, like these calibration things, they're pretty good. I just don't know how much I trust them. Like the construction of them, because I wasn't seeing what I thought I should be seeing, but at the same time that could just be like user error because I have no idea what I'm doing with the NanoVNA. So this morning I just went and created these like my own manual test, I guess, like calibration kit. So here's a 0.1% 50 ohm resistor, 1206 package, and then just a short. I was supposed to add solder joints to this, but I was crunched on time. I don't think it makes that big of a difference. So I'm just gonna plug them in and start calibrating. So we have S11, we have channel 0 plugged in. Sorry, this is also a RF demo kit. So we can go through this to better understand how, like what we're supposed to see across the frequency ranges. However, let's not get into that yet. Let's just, I can start with that, but I think more viewers join like a little bit later, so I'll save that for there. Right now, I'm gonna be like just experimenting a bit, and I think now's a good time while like less people are watching. Here, let's see. So let's start with the short. I did mess up and only buy. Oh no! Oh, I super messed up. I soldered this to a reverse polarity SMA connector. Oh my god. So I have to go and resolder everything. That sucks. Wait, no way. No way. Wait, do I have more SMA connectors? Um, so these were the SMA connectors I meant to solder them to, because these are actually female. I should have checked that. I don't know if I have an adapter, because this is just not how it's supposed to be done. Maybe. Hey, maybe this will work as an adapter. However, no, this definitely won't. That sucks. Okay, I just messed up big time. there goes my calibration kit. I mean, this is just junk now. I can try to, I might make like another calibration kit, but I guess for now we can just trust. I mean, I could load the calibration kit of, let me connect to the device here. So you should be able to see my UI. Connecting to the NanoVNA, and I was playing around with the RF board yesterday. So this is the UFL. Let's do to 150 megahertz. So we have that open. Now, it's not perfect, but I could kind of validate, now that I have like a proper test calibration setting, I can try to validate these calibration loads. So let's start with the 50 ohm load. The dot should go straight to the center. And if it doesn't, that means my load is messed up. You just never know. It's always good to double check. So, okay, where are we at? Yeah, no, that's like, that's very close. 50 ohms, right in the center. I don't know what's the difference between magnitude and Z, like absolute magnitude of Z. Aren't those the same thing? Y. I guess Z and Y are different. Admittance and impedance. It's very interesting. I might stick with the magnitude measurements and argument. I have no idea what I'm doing. So if somebody's like used the NanoVNA in on stream, please like chime in. Yeah, so our 50 ohm load is like 50 ohms. It's pretty good. So I trust the load. I mean, the only thing left to test is really the short. So here's the short. Let's plug that in. We should be seeing, oh, okay. Yeah, series equivalent, 0 ohms. There's just some parasitic capacitance, like a few nanohenries. 20 nanohenries is somewhat significant. But that could just be the differences from the UFL connector and the SMA connector. But we are seeing like an actual short. Okay, so maybe I do trust my calibration kit and it's just user error, like me not understanding how these work. Okay, let's put this. Now I have the short, or sorry, and now I have the open. So I'm gonna measure the open. And yeah, we're seeing a parallel equivalent, a series equivalent of what? That's weird. We have a series equivalent of -7 ohms. I don't know what that means. Maybe I should have paid more attention when they were talking about negative resistance. If anyone in the chat knows what negative resistance even means, please chime in. Okay, I mean, it should be very similar to like not have anything plugged in. So yeah, I think we're just seeing, I guess that's what negative resistance means, but we're seeing negative 5,000 ohms. Let's plug this back in. Shouldn't change too much. Yeah, nothing really changes. It just messes with some of the parasitics. So, and we should kind of see the same thing if we were to measure the, like I just want to make sure we're seeing the same thing. So I'm gonna plug this into the RF demo board. All right, so we just measured our open. Oh, oops. I know things were calibrated for this kit, so yeah, look at that. It's like spot on. I guess our opens, wait, oh, I haven't even plugged it in. That just shows the parasitics are slightly different. This is like spot on, I guess because it was calibrated for this. And And then if we do our short, I mean, it should, we're just seeing a lot of parasitics, I guess. And if I were to load the calibration from the calibration kit, then yeah, this does perform a little bit better. Oh no, it does not. So yeah, it just shows the difference. Oh, hi, Katarp00. How's it going? Thanks for joining. I know it's like, I don't know what time it is for you, but thanks for joining so early on in the stream. Yeah, we're going to be, I don't know how Smith charts work, so I'm going to be kind of learning as I go. I've been playing with this RF demo kit for yesterday, just like I just got in the mail. I've been playing around with it. So I'm kind of understanding a little bit of how it works. From my understanding after measuring like just a capacitor, inductor, this half of the Smith chart, I mean, you have complex impedances that are negative. So on the whole, I think the series capacitance, it means there's like a series capacitance in your circuit. And then on this half, on the top half of the Smith chart, that's showing you have more of like an inductive series, like a series inductance. And I guess everything else in the middle of the Smith chart is when you have a combination of like a series a capacitor and like resistive load, or a series. Well, it's interesting. They don't actually have a series inductive and resistive load, so this isn't a fully complete RF demo kit. Anyways, let's just. I could demonstrate that to show what it means, but I do kind of just want to jump right in and start measuring my antenna here. So I'm going from 2 to 50 megahertz with maybe 300 points. So it should be a pretty large sweep. And what's weird is this is what the Smith chart looks like. Let's see, NFC, NXP, how to measure antenna with NanoVNA. So NFC has a application note on how to actually use a NanoVNA, the exact thing we have right here, to measure our NFC coil. And this, what this is just the NFC coil from my V1 card, a business card. It's like the exact same coil. All I did was put an SMA connector to it. And maybe our connection is wrong, so I'm going to verify the document to see if that's the case. I even populated our 56 picofarad capacitor as well as the IC, because I know the IC has some internal capacitance. So in theory, we should have the exact same circuit. The only difference is these were manufactured on 1 millimeter FR4, whereas this was manufactured on 1.6 millimeter FR4. I don't think it should make that big of a difference because it does change the characteristics of the dielectric, which and then changes the impedance. However, it's like such a small change, and I'm just guessing here because I don't know. I'm not like an expert on the sensitivity analysis of manufacturing materials and how they affect your like your impedance. So yeah, we'll see. I also drew with Sharpie on this board, so maybe that's it. Also, what the heck? That's so cool. You can see through the FR4 here. I don't know if you can see that through the light, but it says KB. That's not from my design. That's just there. I wonder if another. I guess it might change. Katarp is saying that it might change, but it's a very small change. Yeah, exactly. I'm hoping it's a small change. You know, like you would think 0.6 millimeters of dielectric wouldn't be that big of a deal. But this is probably like some marker they had on their FR4. I think if I were to look at another board I have, let's look at, this is the V2. Oh no, it says KB as well over here. Or it says KB. That's interesting. I wonder if that's like, that tells you what sort of material they're using. And I wonder if they have it like all along the bottom of their FR4 panel. And like my board just made it, all my boards made it to the bottom because they're so small. I kind of want to inspect more boards now to see if they all say that. Like this one. Oh wow, that was just a coincidence. No, it says KB right here. I wonder if they label. It says KB in the same, not the same position. They're all put in different positions. You know what? I've never noticed this. Because I usually don't order boards with all the copper cut out. Like this probably costs them a lot of money in etchant because they have to etch away all the copper. But yeah, I normally don't order these boards, so I've never noticed they have markings on the FR4. That's really cool. I kind of want to take a picture of that after the stream. Okay, so this is what we're supposed to be seeing, right? It kind of makes sense. I don't know if it starts inductive or starts capacitive, but it makes sense at like a lower frequency, you're inductive, and then at a certain frequency, you become resistive. Like at the resonant frequency, you're seeing the R and the L. Once it resonates, the signal can pass through. Like at 13.56 megahertz, your signal should be passing through completely. Like there should be very little impedance, meaning there should be a large admittance. In that case, it does make sense to be measuring the impedance and admittance. So this is what we're seeing with the impedance. Very interesting. At the desired frequency, so I tuned this for 14.5. And I mean, obviously we're a little bit off. Like it peaks around here. I guess the load does become resistive, but in a different way. Like their graph, it becomes resistive here. And if I can recall, this is 50 ohms. I don't know if this is 0 or infinity ohms. I mean, if we're looking at the series equivalent, it looks like we're at infinity ohms. We have a picture here. Smith chart. The resistance increases as we go this way. So yeah. So this should be 0 ohms, and this should be infinite ohms. We're looking at a series equivalent of 300 ohms, which is very interesting. That's not what the NXP folks are seeing, or we're seeing like 6,500 ohms at our, I guess, resonant frequency. It does become resistive. So here's where like it's no longer inductive, it's no longer capacitive. Is it calibrated? Yes, I calibrated this earlier with these calibration loads. So in the beginning, I was talking about how I didn't fully trust these calibration, like the open, short, and 50 ohm. So I created my own with a very accurate 0.1% 50 ohm resistor, as well as like a short and an open. However, Qatar, I forgot that I ordered open, short, and 50 are good. Yeah. I forgot that I ordered the reverse polarity SMA connector, so I can't actually calibrate it using my custom load. So right now I'm just putting a lot of trust into the loads that it came with. So this is the short, this is the 50, and this is the open. I have it connected to an adapter, but here you should be able to see. I hope like you can see that on camera. The resistor, I have no idea. So the 50 ohm that I'm testing on, I don't know what its tolerance is, but the resistors I ordered for my own custom kit, this is I can actually pull up the DigiKey order. It's a pretty good resistor. It's 0.1%, so 1206, 0.1%. The thing is, I don't know what its inductance or what its like parasitics looks like at various other frequencies, but here's the data sheet. Look at that thing. I could put it under the microscope, but that's pretty much what it looks like. It's super cool. So yeah, these are like laser trimmed to any value, and then 50 ohms, of course. This is how they make it, I guess. You have a resistive film that's made out of tantalum nitride, and then some barriers, some gold, gold. Yeah. Not that TCR. I guess this is like, I don't know what TCR means. Copilot, what is TCR? I do have like questions for Copilot, so maybe I could just ask Copilot. Oh, Copilot. Okay, it's thinking. Oh yeah, Vishay. I didn't know Vishay was an Indian company. I mean, that's cool. That's super cool. Yeah, they Vishay. I always get their. They have like some high end resistive, some high end passives that I've used in the past. I do really like their um, their products. Here, let's see. Oh, cool. Oh, it's a temperature coefficient resistance. Okay, never mind. I didn't know it was called TCR. I was just like, oh, what's a temp co? Um, it's usually denoted as pipums per degree Celsius. Delta R is equal to R naught, which is the reference temperature, multiplied by the temp co and multiplied by the delta T. I did not know this was the equation for drift. Your resistor drifts by, wow, I did not know that. So it's your temp co multiplied by your reference temperature. So I don't know if your reference temperature is, actually, is this equation even correct? That would be huge. Ppms per degree C. But it's also parts per million. Okay. Interesting. Yeah, it's linear multiplier. Cool, I didn't know that. Also, would this be in Kelvin? No, this is per degree Celsius. But yeah, is R naught, it says 20 degrees Celsius, but the temperature is delta. But R naught is a constant, or I guess. So would it be in absolute scale like Kelvin, or would it be relative to um, Celsius? Because it is the delta, but if you use Kelvin, I mean, that's like 273. Oh. R naught is, well, delta T is the change in temperature, right? So that would be 1, or 23 minus 22. If you were to bump up your environment by 1 degree Celsius, TCR, that's a constant. R naught is a constant. I'm just wondering if this is, I mean, it's telling me it's in degrees Celsius. That's just interesting. I would usually, I'm used to like things being Kelvin, but I think they defined it this way in Celsius. But what if it's like negative? That means at 0 degrees Celsius, your resistance would, like let's say it's minus 40. That means your resistance would decrease. The output is also delta. Yeah. So yeah, I understand that your change in resistance is equal to the change in temperature multiplied by your temp co, which is like 25 pipums per degree Celsius, which is also Kelvin. And then you multiply that by the resistance at a reference temperature. Oh, I'm so stupid. This is the resistance at a reference temperature, not the. I read that as the temperature itself. So sorry. Now it's all making sense. Thanks, Qatar. I think I was just getting hung up on this because I thought it meant the temperature itself, but no, this is like the resistance. Makes sense because it's R. Okay. So the output tells you how much it changes. Yeah, that makes sense. Like, I guess with a certain, like, if you go from 1 degree, from 22 to 23, your resistance would drift by like a very, very, very small amount. Okay, that makes sense. What were we talking about? Yeah, okay. So this is what we're seeing in terms of the impedance. I don't know why the impedance like drastically increases. Is like something not connected on my PCB. At the same time, I've only tested one PCB, so It could be like I designed this board wrong. Trying to understand what could be causing the impedance to go so high. Like, I just want to analyze like how they measured it. Instead of this, I could use a VNA, blah, blah, blah. It's easy to use. We know that. Okay, so they're prepared to cut off the antenna from the tuning circuitry. Oh. Okay, so the resistance of the traces should also be considered. Correct. I mean, I wonder. I do want to look at my stream to see if you can see my desk, because I could draw. But I can also draw with the iPad. So, I want to draw the circuit so we can actually consider the resistance of the traces. The resistance should be pretty minimal because I think I'm using 10 mil traces. So 14.5 megahertz. So this is the one we're measuring right now. I think some things might have gone messed up. Yeah, never mind. All my traces in the board got ripped up, so that's weird. But we could look at the schematic. So we have our NFC coil connected to a capacitor and our SMA cable, and then that goes directly to LA and LB. I guess that means while not powered, LA and LB have like very high resistance, which does explain this chart. I think this just means I'm measuring it wrong, because let me look at, I think they're measuring this without the coil. What the hell? Oops. Oh, what happened? Okay. Okay, so this is the important part. They're soldering onto their tuning capacitors, I guess, but they disconnected their coil. What? On each side of the cutting line, there's an option to solder a single pin row header to reconnect the parts again. Normally, it's a good solution to keep the tuning circuitry connected to the antenna loop, so the major part of the EMC filter and the RX connection assembled on the main board. This part does not normally need to be changed at all, so all tuning can be done on the tuning part, which can be kept to the antenna. With this concept, different antennas with different tunings can easily be connected to the main board without requiring to solder or whatever. The antenna loop can provide a 2-pin row header, so we can measure the loop inductance. Maybe that's what we have to do. We just have to measure the inductance. The TX1 and TX2 can be connected to a female 2-pin header via thin wires. So I messed up and only bought 3 SMA connectors. I should have bought like 10. This is like the first time I screwed myself by buying too few components. So I'll just order a bunch more next time. So this is their calibration kit. Blah, blah, blah. I think they need to explain their setup better. I don't understand. They didn't even draw a schematic of like what they're measuring. Is this a circuit? Measuring the tuning impedance. The same comparison is done with the complete tuning circuitry as derived in 7. Wow, that's helpful. Okay, this shows the tuning circuit with the simulation result. This shows the S11 measurement with the NanoVNA. The results are both good, get enough performance in tuning. So you're measuring through these. This is like the whole tuning circuit, I guess. I guess we have a very different tuning circuit, which is why our results look different. We can also look at this. So this PDF, keep in the chat. See, this is the page I was looking at. They were measuring RLDB. What is RL? So this is what their graph looks like, which is crazy. Like I want it to look like that. And I think, yeah, I'm measuring exactly the same way. So here's the antenna coil, here's the resonant capacitor, there's the NXP chip. So they said assemble the capacitor in design, then measure the resonant frequency at which the impedance is maximum. Oh, okay. So I think we're seeing the exact same thing. Hey, I think we're successful here. It turns out the resonant frequency. So right now we are. This is exactly what I'm saying. I wish they would put the Smith chart as well. But I mean, just from the impedance alone, here's our impedance, here's our admittance. You can see it dips here, so the admittance like increases, which makes sense. This is the resonant, and here's the resonant peak. Unfortunately, I can't. This software sucks, and I can't adjust the scale to see the actual peak itself. But at where it's resonating, we're at like 9.7 megahertz. Yeah. Software. Oh no, OBS. It's funny you mentioned that because now I'm struggling with software. Where's the thing and where's the PDF? Yeah, I know. So if I go to device and then or view as parameters, calibration, I remember you could actually change the graph limits. You could change the graph limits, but it only changes it if it's in decibels. This I think is in ohms. So like for some reason they only implemented it for one section, which is so annoying. So like let's say I change it to 40 decibels or something. It literally does nothing because these are different units. Super annoying. Okay, well, I mean, we're getting a resonant peak. That's good. The only downside is that it's not at 14 megahertz. So if everything was ideal, this is where we would be, our resonant peak would be. But you can see that it's been shifted down here. Now I want to assemble the second antenna so we can we can measure that and see what it looks like. So 13.8 megahertz. Okay, well, at the same time, this kind of sucks because, again, I'm using a 1.6 millimeter FR4. So I don't know if the 1.6 millimeters is what threw the impedance off, is what made it resonate all the way at like 9.7 off of 14.5. That's like, I don't know if that's a big amount or not. So let's, here's the V2. So I'm actually really curious what will happen if we measure it. So I guess we'll assemble it right here. I do need some time to solder it. I'm gonna try to figure out like what that looks like on stream. I'm gonna be like, I guess I have to take you guys outside onto my apartment again. Don't worry, I've improved my setup a bit, just a bit. However, I don't know how good the stream will look while I'm soldering. I just don't want to solder inside my apartment. So here's the SMA connector. Here is the components we need are one NFC IC. So let's pull that out. Actually, I need to get my tweezers. And then we also need the tuning cap. I think that's literally it. We don't need any of the other circuitry. So this is a 22 microfarad. Here, 56 picofarad 0402 tuning cap. And now we just need the stencil, which PCBWay has provided to me. So PCBWay, thank you for sponsoring this video. I've always wanted to be sponsored, so my dream has come true. You know those YouTubers who are like, this video has been sponsored by JLC PCB. Like, that's just like, I was like, wow, I wonder like if I could be cool enough to get sponsored. But apparently, like, as long as you build a project, they're pretty nice about it. So go get sponsored by PCB or JLC PCB. At the end of the day, they want people to be using their service. So yeah, here's the stencil. This is what I love about PCBWay is they easily just, it's like, they're so used to doing this. You just tell them, hey, put the board outline on it, and they do it. Like, look at that. I just have to align these, and boom. This is going to be the easiest board in the world to paste. Yeah. This segue has been brought to you by PCBWay. Yeah, I know. Speaking of segues, our sponsor, the Linus Tech Tips, like segues. He's so good at it. I don't know if I could ever get that good at segues. Okay. So this is going to be super simple pasting. I did move my solder paste to the fridge, so I'm going to have to go get that, which is convenient. Here's my SMD soldering stuff. Sorry, I was going to say, which is inconvenient because now my solder paste is super far away. Only if you start a manufacturing company. Yeah. You know, I kind of want to. I kind of want to start a manufacturing company. PCB fabrication takes way too long. It takes 2 weeks to get a board, which is ridiculous. Like, it shouldn't take that long. I wonder if, like, I mean, Osh Park has done it. Like, everyone's been trying to. It sucks. Like, why can't it be better? I just want it to be faster, you know? Okay, so here, let me go get my solder paste. It's in the fridge. You know, I feel like I buy the wrong solder paste every single time. So I need to improve my process a little, but here you go. And you can see my desk has become very messy very quickly. Hopefully now that it's cold, it's like more rigid. I find my problem with like solder paste in the past, this solder paste specifically, is it's like really wet. It's like, I don't know if it's like the flux is really wet or what, but it just doesn't hold its shape when I paste it, which is why I really like my old solder paste, which I have to throw out because it's like completely dried up. But my old solder paste was a, this one, thermally stable solder paste, 10 lead, synthetic no clean T4 TS391AX50. It was in a jar. But the jar isn't as nice as the syringe. Oh, look, it like heated up so fast that I think it's taking on its regular consistency, which sucks. But also, maybe I just need to get Enig more often. That's all right. We could take a look under the microscope. Hey, I think putting it in the fridge does help. This is better. Like, it normally pools up a lot more. I'm gonna try to bring it up to the camera, but I don't know how well you can see that. So let me do some cleaning first because I hate like having this much. I hate having to clean later. So you're just gonna watch me clean now. Usually use just some isopropyl, pour that onto my towel, like napkin or whatever, and then just wipe the stencil. Oh no. Yeah, this is a mess. Okay, so I cleaned the stencil. That's all good. I just need to clean the blade. Honestly, at this point, I should just not clean the blade and just buy more. I have so many, but just feels bad throwing things away. You know, alcohol's cheaper than blades, and these things last forever because we're not cutting anything. So, and it's just a trip to the store I don't want to make. Like, I have to go to the store. I have to physically move as an electrical engineer. No. No, I'm kidding. Honestly, that's one of the reasons electrical engineering is so hard. You have to move. Like, like I have to move so much to grab things, to find things. Whereas like in software, you could just sit all day and you're always in the zone. You're always like ready to build something. But here it's like, oh no, I have to like move out of the way. Bruh. Katerp. 00. You don't agree with me? Like, I like maybe this is a hot take, but I legitimately think one of the hardest things about electrical engineering is moving. Like once you have inventory and once you build a complex project, like I can store all my projects here in Ziploc bags. It's really easy. But once you get to more complex projects that uses like parts that cross over, you have to start like organizing things. It becomes very difficult. Like space doesn't scale as nicely as software does. You could just like buy a new hard drive. Nah, you gotta build a whole inventory system. You have to like manage it because it's gonna get messed up. The process just sucks. Yeah. Hot take. This is why electrical engineering is hard. So I think in electrical engineering companies, you should have mandatory like morning exercise. So everyone has to like do a run or like push-ups or something. I don't know. Like it's like military camp. No, maybe not military camp. Hardware engineering is not a one-man job, I guess. Yeah, that's true. It at a large scale, just because it doesn't scale well, you know, one person can only do so much. Then you start needing like lots of people. Yeah. Hardware engineering, I've seen some companies get away with remote hardware engineering, and I kind of like that. If you're not building like something hyper complex and big, you can get away with it. And like you just have like, you know, small electronics like this. You have all your employees like working on it on their own. And then you just all meet together when you need to integrate. I just love that model because it gives you so much flexibility. Oh, I need to put my solder paste back in the fridge. See, look at this. I have to like walk over to the fridge. And I'm in an apartment, so everything's like super close. But in like a big industrial area, the fridge is like a good amount away. It messes up your flow. That's just my hot take on electrical engineering. So on one hand, I'm like, it just sucks that I'm putting 2 parts on this PCB and then reflowing it because I'm like, oh, this feels like a waste of time. On the other hand, I'm so happy I'm only putting 2 parts on this PCB because I absolutely hate doing like huge projects. No, I don't hate it. It's fun. It's relaxing, but it does get stressful once like things start. Okay, so pin 1 is here. That makes sense. It's so hard to see on the actual board, but LA is pin 1, and then as you can see, LA is pin 1. Okay, so pin 1 faces up as always. So let's get that on. Sweet. No. Okay. Okay, we got it. I think in this revision, I also added some like extra pins. So we could tap into it if we wanted to. Could measure those pins if we wanted to. What if we build a portable refrigerated, which is IoT enabled? You know what? That's not a bad idea. I know you're kidding, but maybe like I take all bad ideas seriously because that's what needs to happen. I feel like if somebody says it's a bad idea, it means like your field just isn't flexible enough. So a portable IoT refrigerator, like imagine you can, like Samsung has done this where they have like cameras inside the fridge and they have machine learning, but it's so half-assed, like the models suck. But imagine it would be able to like see all your, yeah, Samsung does it. Um, uh, my girlfriend's mom has one, and it thinks like soda cans are like jalapenos. So it's not great. Like the machine learning aspect, I don't think is easy to pull off. But imagine it would like tell you the dates, or maybe it has QR codes, like QR code scanners, because pretty much all electronics we put in, they have like QR codes on them. Like, look at this. It would just scan your electronic parts and be like, hey, this needs to be whatever. Like, you can get like the status of all your solder paste and when they're gonna go bad. So I'm gonna go outside to solder this. I'll try to bring you along. That Japanese vending machine does it. Oh, send the link if you can, because I love watching like Japanese engineering. They're crazy. So let me know if you can, if the signal gets worse, because I've never right now I'm streaming like my camera feed to my computer. Let me get my shoes. So we're gonna solder this outside. Maybe I should reduce my streams to 1.5 hours. I feel like I get tired near the end, but so it's a convenient time for people to pile in. I'll just talk a little slower. Okay, let me know if you can still see. I can't see the comments, so I'm just gonna read. Okay, I'm not seeing any new comments. I hope you can still see. All right, on the bottom right screen. Oh, Katarp says I can see. Okay, I'm like running back and forth. So this is my soldering setup now because I live in an apartment. It's not ideal. I need to get crap. There's like bikes and tripods and everything everywhere. I need to get my hot plate. This is actually, I think the hot air gun might be the fastest, but yeah, whatever. We're not like in the biggest time crunch. I'm trying to figure out like the best way to do all of this. I do have an outlet here, so very lucky, very grateful for that. It's just not great assembling boards at home. I think in the future I'm gonna get more boards assembled outside, which is funny because I also want to buy a PCB mill, so I might end up just like building more boards at home. I'm gonna start not only assembling these boards, but I'm gonna start like milling these boards. So that's gonna get going. Let me go get the SMA connector. So yeah, this was the SMA connector. Let's see. This thing, I don't know if you can see that. Once the NFC IC and the resistor, the 0402 capacitor gets soldered on, I'm going to hand solder this. So I'm just setting up my hand soldering rig. Here's my, I finally bought, is it Hako or Hako? Like a proper soldering sponge thing. That's super nice. Helping hands is nice to have. Oh shit, my helping hands just broke. That's pretty funny. It was some cheapy thing I got from Harbor Freight, so I'm not really surprised. Oh, that's interesting. Interesting construction. Okay, where's it at? Here, let me take you off the tripod. I hope you can still see, but there you go. Let's play the waiting game. Oh, it's pretty hot. So it should like start soldering soon. There's literally 2 components on this board, so I feel like this isn't the first time I've done this. I don't know if you guys seen me on stream build the other one. Also, I can't see your comments right now, so I'm sorry for that. Once I'm done soldering, I will come back and read the comments. I think I saw a little bit of smoke. I guess like when you heat it up, the paste becomes more liquid anyways. So it starts to like, if you were to look really closely right now, I think the paste has turned into like, it's like bleeding into each other. So I guess that's why the curve matters. If you ramp it up fast enough, maybe they don't bridge as easily. Like it totally looks like they're bridging, but I think they're not. I think we're good. Okay, so we're done. I forgot how I'm gonna take it off because it's really hot right now, so just be careful. Oh, it's pretty hot. Who would have guessed? Okay. Now, here's my soldering setup. I guess you guys are going back on the tripod. Sorry, this is just like a super tiny thing on this stream. This is what I got. Here, maybe we could grab it with the helping hands. But I have to be careful not to... I think it's still hot enough for the components to move still, so... There you go. Hey, we did it. Okay. Now, I do want to take this out, or else it's going to melt the plastic. Okay, let that cool down. That's going to take a while. Now we have our SMA connector. You just have to wait for this board to cool down a bit, maybe like fan it. So here, I wonder if you could, if that's a better view. I have no idea what you guys are saying right now, so I also can't communicate with you. I'm sorry, this part, we're cut off from each other, and I just have to trust me. Fuck. Okay, I got that. Got that in there. I did just leave all my solder inside, so I'll reply to some comments. I think you'll see me in the mainstream. Ferk80 says hi, and then Sneaky Pete, bacon, throw some bacon on the hot plate. So hi Ferk80. So it looks like you guys can't see. I do want to throw some bacon on. I'm getting hungry. What was I gonna do? Oh, get my solder stuff. Here. So there should be 2 cameras. I think you could see me holding this. And I'm gonna walk over to where all the soldering stuff is happening in a sec. This is a large through hole part, so I might go with my big solder. Hi everyone, welcome. I think you should be able to see my pinned message. So I'm still playing around with the VNA. Here, let's pull up the VNA results so you guys can look at that in the meantime. Smith charts, whoa. But yeah, so I'm building the V2 right now. First of all, sponsored by PCBWay, so shout out to PCBWay. Yeah, it does look like once it's cooled down, I don't see any solder joints. I think we're good. I'm pretty ready to just start. However, I want to be careful not to pinch the coil. Not that it matters, but just because we have the opportunity not to mess up the board, let's take it. So people ask like what temp you set your soldering iron to. Literally doesn't matter. Just set it to whatever temperature, melts shit. Oh, that's interesting. It didn't get connected to the ground plane. Should be fine. It actually makes our life easier. I set it to 400 because I thought there was a ground plane, but I guess there's not. Oh, this SMA connector itself does have quite a bit of thermal mass, so I might stay at 400. Oh, I forgot to bring my flux. Oh, that sucks. Okay. Let's just get one pin. We just need to like tack one pin. So this is like gymnastics. Trying to solder and hold the thing and not get burned all at the same time. It's challenging. Okay, so let's leave that there, or else the whole thing's gonna fall. See if I could do this without any flux. Yeah, you see, like even at 400, 400 degrees, I think Fahrenheit. Wait, this might be Celsius. Uh, we're seeing it like it's not enough heat to melt, which is annoying. But yeah, I'm going for the outer pins because like the metal's warmed up, which makes it a little bit easier. There you go. I'll go for the middle pin real quick. That should be easy. And then this outer pin right here. Okay. And the last one's optional, but might as well. Whatever. Sweet. Yeah, it's all soldered up. Let's close that. Okay. Tons of smoke. This solder has like a lot of rosin in it. Flux 2.0, which is really nice. Flux 2.0%. We should make Flux 2.0. I'll be so excited. Also, when we think of like what Flux actually is, it's funny. The brand is like Flux because actual Flux is just like this like pasty thing. It's just funny every time I think about it. I'm like, did we know that we named our company after like this pasty thing that people put on their violins? Anyways, we're going back inside. Might wash my hands because I just touched a bunch of lead. TS80, yes, FERC 80. The TS80, I'm using the TS100, which I think is the predecessor to the TS80. Very great soldering iron. I do like it. However, I feel like the TS100 doesn't have enough power. Like some Hakko soldering irons have been better when it comes to those like pesky ground planes. Yeah, it doesn't use a 3.5 jack TS100. So it's a really great project, like this open source soldering iron thing. I just think the designers underestimated how much actual heat you might need to like solder something to a ground plane. Otherwise, I love it. Like I want, a portable soldering iron like this. I might even get a battery for it. Okay, so let me just check the stream so I know what you guys are looking at. Sometimes I just like have no idea what the stream looks like. Okay, cool. So you could you can see things. Just need some feedback. Boom. So here's the V2. This is 13.56. Here's like the moment we've been waiting for, kind of. So let's just like mentally log this. The resonant peak for the version 1. So actually, let me get the two boards. Here's the V1. And here's the V2. So version 1, I duplicated onto this PCB. And what we're seeing is a 9 megahertz frequency response. I want to see if the changes I made to the version 2, I like redid the calcs, I tightened up the traces, I like increased the spacing between them. I want to see if those changes actually change the resonant frequency. So going from 9.7 to a, let's see, might have to recalibrate this as well. Okay. So, whoa! Let's pray to our PCB way God. I love this resonant, the symbol you put Qatar. It's so good. Okay, it's not significantly different. We're looking at 10 megahertz. So either there's like extra parasitics that I'm not I'm not accounting for, because like maybe the dielectric thickness being 1.6 millimeters does move it that much. Maybe it doesn't. Maybe when I calibrated this, there's a ton of parasitics from the actual measurement itself. Because like, don't forget the way we're measuring it in flux. Here, NanoVNA. So here's the 13.56 and here's the 14. So in the 13.56 megahertz board, this is how we're measuring it. So we have these two thin traces going to these vias, which connect to this antenna. I'm really dubious. I'm really like confused now, because the way they measure it is so jank, is like so much worse than how I'm measuring it, right? They literally have, like I integrated my SMA connector into the actual board, and in theory, if I had more SMA connectors, I could calibrate it perfectly to the actual, so I could offset the parasitics of the SMA connector. So I'm learning a few things, like lessons we learned. If I were to make a test board like this ever again, I would also make a second test board, or like a mode where I can just connect the jumper and then put like 50 ohm resistors, shorts or opens. So you can really calibrate for all the parasitics that show up here. If I could do this all over again. To like, I don't know, are the parasitics actually that ground plane not separated? Yeah, it could be the ground plane. Like, I don't know why the ground plane, if you look at the real physical board, the ground plane got like eaten up on this one. So in the first board, I put the traces on top, and the second board, I put them on the bottom. However, in this specific board, under the SMA, the ground planes got separated. There's like just a ton of copper here. You know, that's possible. Maybe there's like this copper here is like, there's some RF that's like resonating or something. I have no idea about deep EE. What do you use VNA for? Detecting signals like real world usage. Yeah, so let me kind of give a whole broad explanation again with what we're doing with the VNA. So if I'm not mistaken, I also don't know how VNA like works at a nitty gritty, but in theory, what it should be doing is passing through a ton of signals. Like here, we can set our sweep parameters from 2 to 50 megahertz with 300 points, meaning the step size is 160 kilohertz. So so at 2 megahertz and then 2.16 megahertz, 2.32 megahertz, we're putting a sine wave through the circuit and measuring the reflection, like what we get on when it comes back. And then you could go into transmission line theory, but basically at all these points from 2 megahertz, like you can see the frequency down here from 2 all the way to 50, we're inputting, we're measuring what the circuit looks like. And on the Smith chart, it just kind of tells you how inductive or capacitive it is and what the impedance is. So right here in the center of the Smith chart is 50 ohms. Here is infinity ohms, and here is like 0 ohms. And then everywhere here on the Smith chart corresponds to at what frequency, at this frequency, what does the circuit look like? So at 22 megahertz, it looks very inductive. Like you can even see the series equivalent has 2.5 microhenries, which I think is I tuned the inductor to have 2.4 microhenries. So this is pretty accurate. And we have a 1 ohm resistance, which kind of makes sense because the coil itself is a short. Does that make sense? I think that makes sense. The coil is just shorted. So we're seeing a low resistance. Katarp00, earlier you said, let's think about the series resistance. This is probably the series resistance, like 1 ohm, 1.4 ohm, something like that. As you can see, the resistance increases as we get closer to here. So what you're seeing is the circuit looks inductive, and then over here, the circuit looks capacitive. However, right in the middle is where the circuit is not capacitive or inductive because the capacitive and inductive elements are resonating. So right here, if we want to look at the circuit, we have, I think this is the actual circuit we're looking at. We have some R connect. So this is what Katarp00 was talking about, the R connectivity. These are parasitics from the traces or the connection or whatever. We have the capacitance of the IC. We have the capacitance of the connection, whatever. That's like pretty minimal. And then this is CA. This is like a large capacitance that we added, which is 56 picofarads. And then RA, this is also the resistance of the coil, and LA, which is the inductance of the coil. So what we have are, we're measuring a parallel capacitance and a parallel inductance with the VNA. Here it is. And we can actually see this. So VNA. So we can't actually see, oh no, the signal is degrading. What's happening? I think I was just like touching it, so I messed it up. Okay, so yeah, you can see it doing the sweeps. So you can see here we're inductive and here we're capacitive. So those are the two elements we're seeing. We're seeing the parallel capacitance, which is 100. It's about, see over here, it's about 106 picofarads. That's exactly what we said. We put 106 picofarads here. And then over here, we're seeing about 2.5 microhenry parallel equivalent. So over there, like the other capacitive and inductive elements aren't like interfering, but at just the right frequency, they resonate and they have very little impedance, which is why you can see the admittance like decrease, I guess. Anyways, okay, so you can very sensitively check your PCBs. Yeah, so 50 ohms is like 100 ohms in parallel. Thank you for the explanation. Let me just go through those one by one. Also, I want to answer Katarp's question after I'm done with this about the ground plane not separated, because we're trying to diagnose why the resonant frequency is so off. So yeah, first let me answer FERC 80. So you can very sensitively check your PCBs. You can measure, specifically what we're doing is measuring the impedance, the complex impedance, which is like what its parallel equivalent, what its series and parallel, like up here, the series and parallel inductance and capacitance looks like across a frequency range. So yeah, from 2 megahertz to 50 megahertz, this is what it looks like. This is what it actually looks like. If you put a 1 microfarad capacitor, it's 1 microfarad at one very specific frequency. At every other frequency, it will behave very differently. So what we're doing is seeing how it actually behaves. And then yeah, Katarp is saying, so 50 ohms is like 100 ohms in parallel. Yeah, that's true too. Like this. Yeah, I'm not fully following, but yeah, 50 ohms is, yeah, you can have, I guess also that just shows that when you put things together, we're measuring like the effective equivalence circuit, which is why it says like series and parallel equivalent up here. And then Katarp is saying the ground plane is not separated in this board, or the ground plane is separated. This could be a problem, especially on the bottom layer. It looks pretty bad. The thing is, I've never dealt with, here, let's turn off the top layer so we can just look at that. Like, look at that. That looks so weird. I saw that on the actual board too, and it looks like super weird. That's one thing that sucks is like, I think I didn't define this as ground, which is why the ground plane does this. But what it sucks, I can't just like delete islands, or Flux doesn't have the capability of deleting islands yet. And I see, I just don't know that much about electromagnetic theory to do a sensitivity analysis to be like, hey, I wonder if like this is causing our our frequencies to shift. I just don't know. My best guess, I mean, the ground planes should be separated by via stitching. Oh, that's what you meant. So yeah, in this design at least they have via stitching. I think I even put a stitching via here to make sure this island is grounded. And then this big pin from this 4-pin connector I added, this should also have stitched the planes together. So they should actually both be ground. Um, does that make sense? It's also very interesting that Flex doesn't consider this as like, it is internally shorted by these traces, but it's cool because this creates like an inductance. And it's thinking that, oh, you have to actually like short them together. But it's like, they are technically shorted by a bunch of traces, but I am creating like an electromagnetic impedance at high enough frequencies. Island for underground antenna. Oh. I did a cutout under the antenna. Island for ground under antenna. Yeah, so in the actual PCB, there's just no copper on above or below this antenna. SMA. SMA. My bad. Yeah. Oh, so you're saying these the ground here isn't actually stitched. So let's look at the bottom layer again. Yeah. So that's just floating copper. It's not connected at all. Yeah, I don't know the effect. I don't know what that is. The thing is, it's inconsistent on the V1 board. I don't know if you can see it, but I put the trace on top, so the ground is actually mostly connected. Oh no, I take that back. Yeah, there is one piece of floating copper on the V1. However, there are like 4 pieces of floating copper on the V2 because I put the traces on the bottom layer. So I guess the best way to mitigate for all this is just to calibrate for all these. Oh, basically what we're talking about are like these ground plane issues, all these things. Oh, and here, Qatarp 00. I think you might have been pointing at this. This is unconnected. This is floating copper. This is floating copper. This is ground, but yeah, this is just floating copper. So these could be contributing to parasitics. The best thing to do is just in the future, if I were to build one of these boards, I would actually put page 18. Okay, let's check it out. I would just put like the what's it called? I would put the calibration resistors on the same board, so we calibrate for all the problems. Anyways, the ground layer is extremely important for RF PCB design. The return path is the ground beneath the RF trace. For good RF performance, the return path should be uninterrupted as wide as possible. Correct. Yeah. What's it called? A really good video for this. Robert Furneck, crosstalk, return path. So this isn't RF, but I mean these frequencies are at like RF frequencies. If y'all want to get deep into it, this is why the ground plane is very important, especially at high frequencies. So you know what, Qatarp 00, I think you're right. Like it could be the lack of a ground plane, the lack of a return path. So the return path in the coax cable going to the SMA connector is actually pretty solid. Like these 4 pins are technically ground. It's return path. However, let's see. Let's analyze where the signal goes. So the main signal goes here. There's no return path other than this. This is the return path. The thing is, I didn't want to ground the SMA connector because LA and LB, we're measuring something, we're measuring almost like a floating circuit relative to the ground of the IC. So I use ground as the reference for the IC. I could have chosen ground to be the LB of the IC. However, you would create a massive like reference plane. So I don't know how if that's bad or anyway, but it would definitely change the inductance characteristics of the loop. I think the loop inductance is set by the fact that, you know, like there's no ground plane with it. If you added a ground plane, it would drastically change the inductance properties of the loop. So almost the fact that it's like a bad design, almost it behaves like inductor. It's just more predictable this way. The return path is really short. If you were to actually measure out how long this is, it's probably a few millimeters. I think it does make a difference at like higher frequencies, but we're in a relatively low frequency. Like I think, you know, at 13 megahertz, you're not looking at like I don't think the parasitics introduced by having a poor return path. So yeah, Qatar 00, I do have a poor return path here. But for such a short distance at such a low frequency, yeah, you're saying it's a very low frequency. At 10 megahertz, I don't think it would cause like a 4 megahertz shift. So my best guess is just we're seeing some uncalibrated parasitics here. It's throwing us off a bit. Maybe we need to put more like measurement points. But what's very interesting is actually the fact that, what was I going to say? The fact that we did shift. So we went from 9.7 megahertz to 10.2 megahertz. However, it's really funny because on my V2 board, I wanted to go down. So the V1 was tuned for 14.5. The V2 was tuned for 13.56. So maybe the tolerance is just so bad that what's like explaining the tolerance is 32% difference is weird. Yeah, it is weird, right? If it's tuned for 14.5, why is it at 9.7? Like there should be a big explanation for this. I wonder if it really is just the thickness of the PCB. So I'm going to say this was just bad measurement. I think I just measured this kind of poorly. And if I were to do it all over again, which maybe I should, maybe I shouldn't, I don't know if it's worth the time. I think it is because I'm just interested in it. If it's worth the time to remeasure everything, I think I might I might do the setup differently. At the same time, I just realized this is kind of weird. Why does the impedance peak here? Shouldn't the impedance be on this side? Shouldn't be at 0 ohms because we have a series equivalent of 5,000 ohms at the resonant frequency. But if you think about the coil, it's just a short. So if the capacitive and resistive element, if the capacitive and inductive elements are resonating, allowing that sine wave to pass through, like at the resonant frequency, you could think of them as almost like shorts. Then why is the resistive load so high? Like when we were measuring the resistive load out here, we're seeing like 1 ohm, 2 ohms, maybe 3 ohms. Why does it all of a sudden hit like 5,000 ohms? Does this coil have that high of a resistance at that frequency? I mean, it does. We're measuring it. It's just like my theory is just like very off, you know? I think I'm not understanding the theory very well. However, it does coincide with what these guys are measuring. It's kind of weird because they're measuring, Z ohms. Okay. So they are measuring the impedance in ohms. And they're seeing, like 5,000. Well, we just have like the exact same graph. Okay, so they're seeing a 5,000 ohm peak here. However, their frequency is very on point. So the only thing I did different is that I had a 1.6 millimeter PCB, and maybe PCBWay's dielectric constant is very off. Like it's possible that the dielectric constant they quoted me at like 4.3 is just like way off, and it's like 4 point whatever, it's like 5 or 2 or whatever. Like, but it's like maybe the tolerance on that is just wildly off. Maybe calibration. Yeah, and the calibration was really bad. I like calibrated on these things with, you know what, Qatar Zero, I think it is calibration because the way I calibrated it, I used these loads using an adapter. So this adapter does add its own parasitics, and we're talking about like picofarads here. Like I know we're at hundreds of picofarads. Okay, so actually no, I'm kind of, you're saying, so we have a 32% difference. It's weird that if I had to estimate, this SMA coax adapter probably adds like 5, 6 picofarads at max, maybe 10 picofarads. But that's like 10% of our total capacitance. We're looking at 106 picofarads. Um, so 10% shouldn't, the calibration shouldn't add to 30%. Yeah, you need to add the offset for the adapter. Um, so yeah, again, Qatar 0. If I were to do this again, I would mimic, if I could calibrate it as perfectly as possible, I would just create a second board where my resistors are right here. So I calibrate for these traces too. These traces are taken into account for my calibration. So I don't remember for the NanoVNA. Yeah, I also don't remember like how to add offsets. I think it might be in here. Device. I think in fine tune, you might be able to add offsets or something. So you could shorten the length, open length, load parasitics. So yeah, you can actually fine tune it. However, I'm just guessing at this point. I'm not an RF. Like I don't even know what happens at 14.5 megahertz, or 13.56 megahertz. Um, Cypress. So yeah, if I might do a second board rev of this of measurement, because measurement is very important, and it's important to like incorporate your learnings when measuring things. That's just how I could do things better, but I'm still not able to explain the 30%. Maybe, Qatar 0, maybe it's a combination of everything. So calibration, let's say it's calibration, like calibration adds 10% to our deviance. And then let's say the 1.6 millimeters adds like another 10%. So we're at 20%. The thickness of the traces, also the thickness of the traces. Yes, when I designed this board, I actually took into the account of the thickness of the traces. Um, the thickness of these traces are very, very like selected. Like these are selective. This gives us the inductance. The thickness of these traces, however, are not selected. So everything here, I think it's been accounted for. The calculator I used assumes this adds like 3 to 4 picofarads of parasitics. So I'm gonna say that we've already accounted for it. At least these traces. These traces we haven't been counted for. And then maybe this adds the extra like 5-10%. These might add enough. So altogether, maybe the factor of like the 1.6 millimeter PCB plus the calibration being off, which I guess is this. This is the calibration being off. So those two factors alone, I think, might be contributing to a total of 30%. Like it's the only explanation I could come up with. Like how else is it? I think the calibration could add more, because if you think about it, I think the calibration, it's 10% from it's potentially 10% from this calibration adapter, and then it's another potential like 5 to 10% from these traces that Katarp was talking about. The thickness of these traces, these could be contributing to the last. Also, like Katarp was saying, there's no ground plane here. There's no reference plane. So the return path is like, it's creating like the loop created from this area right here. The distance from here to here. That creates some capacitance, like here, just to illustrate my point more. Like there's a capacitance here. This creates, its own parasitics. So yeah, if I had to guess, all these problems contribute to our total. Also, the 1.6 millimeters might actually contribute a larger amount. So if we're going from 1.6 to 1 millimeter, zero point 0.6 is literally 60% difference in dielectric thickness. I know the dielectric doesn't have that massive of a impact, and let's go ST NFC coil design suite. I forgot what it's called. Can you probe to the via? Do you mean like can I solder onto the via and then connect it to my VNA? Um, I cannot probe to the vias, but there are two terminals here. So these two tiny terminals, I can actually solder to this. Yeah, the vias are tented in my board, unfortunately. So, but I can solder to this. It's just going to be really hard because these are like 0.3 millimeters. FERC 80 says it would be nice if Flux could simulate electricity going through and predicting measurements. So you bypass the SMA. Katarp 00, I could. Yes, you're right. I could. In fact, it'd be easier to solder onto the capacitor, but it would just probably take me 30 minutes. And yeah, maybe I'll do that after this live stream. I'll try that if I have time. So to answer FERC's question, I actually do have. Where are? Oh no, all my notes. Here, I'm gonna look for them. Oh, here. Actually, we could just go to Jonathan's webpage. So this probably isn't going to go anywhere, but Jonathan has built some crazy cool stuff. So check this out. Try it when you're free. Yeah, I might give that a shot. So FERC 80, there is actually a simulator coming. Wait, what the heck? Where'd it go? Oh, this is the display itself. Okay. This is it. This is super cool. Check this out. So I think it just takes a little bit of time to kick in because it's like kind of a beefy simulation. But these AND gates will simulate the signals on this circuit exactly. So Flex is building this. It just takes a lot more time to define the characteristics across the frequency range at these frequencies. Is this like Falstad on Flux? I don't know what Falstad is. Let me search it up. Whoa, this is cool. Yo, it's like I think I've seen like implementations of this. This is awesome. Interesting enough, Flux currently has something like Falstad, but this is a whole overhaul. This is an entire overhaul that has Spice in it. I don't know if I should be telling you guys this because like we don't know the state of when it's going to launch. I don't know why the simulation hasn't started yet. I think like reset the simulator. Okay, so something might have broken. See, this is like, I wish I could show you because this is so cool. When you can see all the signals on all the pins, and then you can start seeing the 7-segment like change and stuff. So unfortunately, it is not working at the moment. So that's a bummer. Let's see if there's something else that does work. This might work. It's funny because Jonathan doesn't rename his project, so I don't know which ones are actually like really cool. Interactive 8-bit LED adder, 8-bit adder. He has like, I also did a PID thing. Oh, is this not working? Yo, check it out. Like this is the simulator. So it's actually passing things between these registers, and it's like Go Flux is like simulating the whole circuit. Whoa, I never even saw this one. And the LEDs changed too. It's like showing you the clock. Unfortunately, I can't see all the signals here because we're not measuring them, but like normally you can. Anyways, Probably not. FERC80, I'm absorbing so much knowledge. This is great. I love it. Yeah, dude, join me on the streams. Oh, check it out. Here's the adder. Oh, Jonathan, break out the signals. I think the reason we're not breaking out the signals is because it's really funny. The spice is really fast. Like the spice simulation is really fast, but showing these signals takes so much like compute resources. So this is like, I think the reason Jonathan's not showing them is because this would actually like massively slow down the simulation if we like showed all the signals, which is probably what's happening in the other one. This one just needs some time to start up, but you will, once it does start, you'll see the LEDs start counting up. I think my computer might just be too slow, like to show all the signals, because I remember these projects that Jonathan built have like, you have to like they do show all the signals on each pin, and that is what takes a lot of compute resources, not the actual simulation itself. That is like solid. This one doesn't do anything. Come on. I think also this is under active development. So this is like, this is going to take some time. That it's probably broken. No, it doesn't have Verilog. So everything's in system code. But down the road, we want to support Verilog. That would be freaking awesome. So how it works is, it's just a spice simulator, except you could define custom models. So upon each step in a time domain analysis and down the road, maybe even frequency domain analysis, you can change the parameters of your parts because we create an interface to the part itself. Parts are usually written in C for spice, but you can redefine what's happening. So I think actually, it's not Verilog. What's actually happening here is Jonathan is creating like MOSFET AND gates. Like he's creating CMOS gates using transistor models. So this is a full analog simulation. However, down the road, Jonathan, like if you want to speed up how fast this works, you might want to define your own logic gates with its own like time delays or whatever. Like, this just like, you can't build a super complicated circuit because you have to simulate the analog signals at every time step, and it's just gonna have so many transistors. Probably need a supercomputer to do it. But yeah, like Verilog is the next step, right? By simulating that, by like abstracting these analog gates into actually like their parameters, like, oh, these have X, Y, Z time delay. It makes it a lot easier to simulate complex projects. But there's nothing stopping you from defining it because you can have custom models. I think, so I also had a project that was like a PID model. I should also open Jonathan's because I think he's the one who actually implemented it for me. But I created a custom PID model. Okay, so I didn't actually integrate it. Jonathan is saying, where's Jonathan? PID. And then FERC80, wouldn't it be possible to wire up a virtual PCB to a real one? It would. Also, check this out. The PID controller is working. So it's regulating right now. If we restart the simulator, you can see it like bounce back. But yeah, see, it's slowly regulating. Obviously, I didn't tune the KP, KI, KD very well because it's oscillating like crazy. But it does eventually regulate to like a certain voltage. So this is like a PID controller that does actually work in the simulator. And then FERC80 is saying, wouldn't it be possible to wire up a virtual PCB to roll on? Yes, so there are some, oh wait, I think Flux AI / JLAM Flux. Jeffrey has, oh, let's do a Kalman filter on Flux. Yes, you could totally do a Kalman filter. This is crazy. So the simulation I showed you, FERC80, you're saying wouldn't it be possible to wire a virtual PCB to roll on. This was the simulation that was done, and this simulator should work at some point. What is this? Okay, that is just a bug. Oh, dude, it's working. Let's go. It's in prod. No way. Okay. Yeah, check this out. So the simulator is counting up. 1, 2. Okay, I think something in the simulation broke because it's like counting from 2 to 7, or it's counting so fast we can't see it and we can only see 7. It's like aliasing. But there's actually a PCB for this. So you can go and manufacture this and hook it up and actually see the behavior in real life. Here's the 3D view as well. With enough code automation and APIs, yeah, I really want there to be like, so FERC 80, I had this idea where Flux automatically goes into your board. It generates a ton of like test points all over your board, and you can automatically generate scripts that just check your simulation and then check the actual board and find differences. You just do a diff check. It's like, oh, what's the difference between the simulation response and the real world response when I give it an impulse response or like an I2C signal or this command or whatever, and then Katarp 00, you're like, oh, just kidding. Like you could totally do a Kalman filter, especially down the road if we support like custom or simulating microcontrollers within Flux. You can totally implement a digital Kalman filter. I don't even know if you could have like analog Kalman filters. But yeah, you could totally have like a digital Kalman filter and then run that in simulation. So let's take the geometry I currently have. I think I have 5 turns. I have this. Oh no, it wants me to log in. This is so annoying. Come on, ST. Why you gotta do this to me? Okay. Numbers. So this is round. This is round. This is square. So this was what I used to actually find the numbers for my NFC tag. I'm just curious. So I'm gonna loop back to the NFC stuff. I'm just curious to see. This is the 14.5 megahertz. So I have another one that's 13.56. But I'm curious to see with these parameters, how big of a difference 1.6 millimeters gives us, according to theory. We have, I think the one I went with was 5 turns, 300 micrometer antenna length. Oh, I think I did 40 by 40. Width is 0.3, and then the spacing is also 0.3, I believe. In the 13.56 megahertz coil, I had like 400 micrometer spacing, I think. And then what is this? Number of turns, turn exponent, whatever. Thickness, 35 micrometers. So if we do 1, we're at 2.57 microhenries. And then if we do, is that my target? It's funny because this is 2.11, so something here is wrong. If we do like 1.6 millimeters, no, the thickness does not change it at all. I think it was 4.6. I can't remember the dielectric constant that PCBWay quoted. Also, like looking at it, the dielectric constant has like almost no impact. Like if I do 2, it literally doesn't change. If I do 5, literally doesn't change. 6. Okay, you have to change it to like 6. There's no way it's that different. I think the tolerance is pretty good. So now I'm extra confused. Like, I do like a 20 millimeter thick board. It has no impact. 0.6 millimeters has no impact. Let's say like 1.6. Yeah, no, the thickness of the substrate has virtually no impact on the actual coil itself. And then I think for the 13.56 megahertz coil, here's the 13.56 numbers. So we're looking at 420, 626. I had 6 turns. Interesting. I thought I only had 5 turns. Maybe that's why it's messed up, because I calculated 6. 1, 2, 3, 4, 5. I have 5 turns. Did I mess something? Oh, did I mess it up by calculating 6 turns? I only put 5 turns. That's seriously, that's really bad. Wait, hold up. No way. 420, 620, 2.41. I missed a whole turn. Wow. That explains so much. You know what? I need to do a V3. Oh my god. Oh, 300 and 800. No way. Is that actually what happened? So I did 420, 620, 0.42, 0.62. We're looking at 2.59. Wait, maybe I did 5 turns. 2.12 microhenries. What are the actual specs on my antenna? Now I'm curious. Okay, I think I just need to open it. Wow, so I definitely messed up. Now I need to add a comment saying don't use this part. Okay. So the thickness is 300 micrometers. Oh, so I think I used one of these ones. Now what's the spacing between them? So 17.87, 17.16. What? 17.87, 17.16. So we're at 0.71 minus 0.3. So we have 410, so 0.41 spacing, and we have 0.3. So I think I might have done something. Yeah, 2.4 microhenries. And this is a 2. No, this is correct. So at 13.56 micro. So I did the calculation somewhere and it was like completely off. But whatever. We have a 2.41 microhenry inductor at 13.56 megahertz. And then Qatar is saying the outermost turn, it will be around 15 to 16%. Is the outermost turn, then it will be. So are you saying the outermost turn is contributing to my parasitics like this? Maybe it's like 13 to 15%. I doubt it. But yeah, Qatar isn't. I can't remember, Qatar, where you worked. I think we all kind of popped in with the industry we worked in, which is super awesome that we could all jam like that. But yeah, according to the theory, I didn't mess up. Things are still correct. Yeah, that sucks. Maybe I did the math wrong. Resonant frequency formula, RLC frequency calculator. Okay, so we have 2.41 microfarads. What? Oh, this is, sorry, we have picofarads here. So 106 picofarads. I think it's nanohenries. No, we're at microhenries. So that's a lot of henries. 2.41. Was I supposed to target nanohenries? There's no way. Let's say like 2 ohms. I'm not sure where the issue is. Yeah, Qatar 0. I'm struggling too. Hey, no, this is the issue. I found it. According to my circuit, so the calculator was wrong. Don't trust the calculator. According to the calculator, this gets me a resonant frequency of 13.56 megahertz. But according to the actual RLC circuit, like we're at 9.9, which is exactly what we're seeing. We're seeing like a 9 point, like here. So I just designed it poorly. That makes so much sense. So there's actually no parasitics here. Like we're at like 10 megahertz, which is very, very close to 9.9. This is like, wow. So I designed my board perfectly. I just trusted the calculator, which spit out wrong numbers. This is great. At least we figured it out. I guess we have to do a V3. Mind blown. I know. We have to do a V3 now. Okay, so let's say we have like 2 microhenries. That gets us closer, like 1.4. So it looks like with 106 picofarads, we need to be at 1.3 microhenries to get there. Why did I ever trust the calculator? Okay, if let's say we can't change the coil. If we go 50 picofarads, hey, if we remove the capacitor, my circuit should work a lot better. We have 10 minutes left. You know what? I think I'm going to remove the capacitor because that brings us to 56 picofarads. Wait, no, that brings us to 50. Then we're at 14.5 megahertz. I could go and buy a 7 picofarad capacitor, and that should get us to, so wait, let's do it, DigiKey. First of all, let me just add this to my cart so I don't forget to buy a 7 picofarad capacitor. So I need to bust out my hot air gun. So 7, about like 6 to 7 or 8 even. Let's just, I want 7. Please give me a 7 picofarad. Or like 6.5. No, you can buy 0402 7 picofarad caps. Okay, I'm going to add it to my cart and then order my next order. I'm glad we checked it. Okay, let's change this impedance just to be sure. No, changing the resistance only changes your Q factor, which makes a lot of sense. Even if we have 5,000 ohms, it just changes your Q factor. Okay, let's do it. Let's remove the capacitor, and in theory, these boards should work better. These are the only boards I have, so they're only gonna get better from here on out. I think we could do it. However, I can't test it and show you guys me testing it at the same time because I need my phone to test it. It's one downside of having massively useful equipment is when you have to use both its functions at the same time. Okay. I forgot to bring my tweezers, which is important. Always corroborate so I guess the lesson learned here is to always corroborate your data. I'm thinking these capacitors are so tiny, I could just remove it with a soldering iron. I don't need my hot air gun, but I do like my hot air gun. I think I'm gonna use the hot air gun. It's just like the proper tool for this job. It's like stuck on something. It also heats up really fast too, and cools down really fast. This thing's awesome. The tip just fell off, so I need to grab that. You know what? If this works, I'm gonna be so disappointed in I'm gonna be really happy that it works and I just improved the design. But I'm also gonna be somewhat upset that NXP, they probably had some application engineering interns that wrote this. They wrote this guide on how to do this, and they just did a bad job. What? Why is there no power? I think, oh, this is disconnected. Okay, boom. We got everything. We got the tweezers. I don't know how well you guys can see or hear me. I do have my lavalier mic, so you should be able to hear me no problem. No! I dropped my tweezers. Oh, this is horrible. Okay. This should be really easy to do. Yeah, done. Removed one. This is like doing surgery on a grape. Okay. Moved the other one. We're done. We just removed both caps. See, this is great. Where's the tip protector? Put that back on. Caps are off. We can always put these back on later. They're so cheap. Just throw them off the balcony. Don't tell anyone I did that. Okay, let me put this crap back. I think I need to keep this on so it can cool down. Yeah. This is a mess. You know, I'll come in and clean this later. This is for your viewing enjoyment because we have like 5 minutes left. Okay. Let's go. I doubted the ground plane. No, that's funny. No, it's good. I mean, I appreciate it, Katarp00 for piping in your ideas because we need ideas. Definitely need ideas. So I'm going to turn off the stream from my phone so that I can actually tap the NFC coil. So you guys shouldn't be seeing anything. Let's see if this works any better. So, oh my God, it does. Wait, this one works better. Check it out. I mean, this is already more responsive. Okay, it's not perfect. Maybe I just got the angle like just right. No, okay, this one still sucks. Let's see the new one if that works any better. Oh, that is like night and day. Wait. Also, I'm stupid. I should have removed it from the test board so we can actually measure it using the VNA. Yeah, look at that. The light's a lot greener. Yeah, that feels better. That feels better. Look at that. Oh, that is so good. I can just bring it up. Wait. Yeah, that is more reliable. So I think if I just took the capacitors off, good thing I didn't clean up because we still have some ways to go. Also, I just put my phone in my pocket. So here, can you guys see? Let me check the OBS. Okay, yeah, you guys should be able to see. I'm gonna go remove the capacitors from the test boards too, and then I might stay on just like a few more minutes so we can measure the frequency. Maybe, you know, once we remove it, maybe we'll get up to like 13 or whatever megahertz. Oh, oops, forgot to bring my tweezers again. Keep forgetting. Here we go. Okay, so this is the, here we have the V1. Sorry, I don't know how well you guys can see this. Here's the V1, here's the V2. Yeah, you could tell because I had an 0603 pad. Okay. I don't know why I put that in there. 0402 caps. Boom. Okay. Oh, I could let that cool down. I don't know how NXP, in their PowerPoint slide, they did actually put 100 picofarads in parallel, or in parallel. So I don't know how they got such massively different numbers. But now I know I can trust the the NanoVNA. This thing is absolutely awesome and it's great. I don't have to make my own calibration tools anymore. So it's awesome that we can diagnose this. Let's see, can y'all still see what's going on? Should be able to see my screen because that's what I'm streaming. Also, hope y'all can hear me. Let me know if any technical issues happen. We might have to reapply this because it's still resonating around. Oh, no, the resonant peak is still. Oh, thanks, FERC80. Here, let's disconnect this. Oh yeah, it's just not scanning, so I have to like reconnect to it or something. Device. This happens sometimes. Good thing I streamed all this, so I don't have to document it later. I can just take screenshots from the stream, which is amazing. You know, all EEs should just stream what they do because then they don't have to document. Okay, it looks like the app's gonna want to freeze on us, so let's force quit it. Sorry about the ads. I just that's the cost. That's the cost to not having to, what's it called? All the ads, not remembering anything from school. Okay, so it's gonna be, I think it might have froze. Okay. Mac confuses me the most. Yeah, that's true. I used to be like a Windows boy. But I gotta say, there's some features, integration features that I just can't let go of. Like being able to copy paste across devices, so good. Linux, yeah. Okay, that's true. Linux is the way to go. It just takes too long to set up. It's like a guilty pleasure of mine to set up Linux systems. Let's go 20 megahertz, you know? Why not? So this will look different from the other one. But let's measure the impedance as well as, I guess, the admittance. Why not? Oh, wow, that is a huge peak. Yeah, look at that. We are right in the 13. Oh, okay, so this is the V. Which one is this? This is the V1. The V1 resonates, like, it does. Who uses Windows? Yeah, I know, Windows is trash. No, I'm sorry, FERC80, if you use Windows. I don't know what you use, but Windows is so trash. Okay, so we're looking at a resonant frequency of about 14 megahertz on the V1. So yeah, that's pretty good. Like looking at all the parasitics, 14 megahertz on the V1, that's pretty accurate considering if we actually take the real inductance. So right now we have about a 53, in theory we have 53 or 54. And I can't remember the inductance of the first one. Let's see. NFC antenna. Shit, if I if I actually knew the inductance of the first one, I could guess, but I don't actually know. Crap. I didn't document it. So it might be like 2.3, whatever. So I'm not surprised to see we're resonant at 14 megahertz. However, we do know this, so we should also see 14 megahertz on the V2. So I literally just made a V2 for nothing because nothing's changed. Looking at about 13. So in theory, you know, we're predicting 14-ish megahertz. Okay. The resonant frequency is actually at 14.5. That is so funny that my V2, I tried getting closer to 13.5 megahertz. But in fact, I just got closer to 14.5 megahertz. So in theory, if I bumped up the capacitance to like 60 picos or like 68 picos, so we're at like 53-ish, which gets us, well, we're at 14.5. So what that means is our capacitance is actually, oh, so we have like no parasitics. So I laid this board out pretty well. Assuming the inductance is actually 2.4 microhenries, let's go here and like see. No, we're at like 2.69 microhenries. So it's not the capacitance. However, the equivalent capacitance is 50 picofarads. So if I bumped it up by 7, 8. Yeah, if I bought a 7, 8 picofarad capacitor, we would be right at the 13.5 microhenry resonant frequency. So this is like how real tuning happens, I guess. You measure your circuit, you realize you screwed up. And yeah. Thank you all for joining. We're 5 minutes over. I'm going to go have lunch. Thank you, Katarb00. Always is being here. And Ferk80, welcome. I'm glad you learned a lot. You're always welcome. Ask any questions you want. I'd love to explain it, no matter how complicated or simple they are. They're always great questions. So yeah, thank you. Thank you all for joining. I'll see you guys next week. Peace. And you'll see me exit.